as we start this, what the real focus of all this has been brought about, because as we work on farms, farmers say, look, I got a problem. Everything that we have developed here is simply to try to address and correct the problem. There's nothing theoretical here. We've done this over and over and over. We've got the sunburns, we've got the frostbite, we've got the mosquito bites. We've been rained on and hailed on and snowed on to do this. And so this is all coming from first-hand experience just to solve a problem. And so there's nothing any more grand about this whole design except farmers have said, look, something's not working, help me figure it out. And the gentleman that I work with lives there in Logan also, and he formulates specialty products. We're not in the business of selling NPK. We're in the business of trying to efficiently manage minerals and manage biology. And so our direction is to improve what you would normally buy to operate on your farm. And when you think about this, your fertilizer costs are your largest ongoing expense year after year. And what happens is, most of the fertilizer that we buy will never see the inside of the plant. When fertilizers are made and put together, these elements have reaction periods. And some of them tie up very, very quickly. Some of them last a little bit longer. But the bulk of what you buy doesn't stay available long enough to go into your plant. So you buy a tractor, you use it for 5 or 10 years. You put up a building, it's good for 20 to 30 to 40 years. You buy a fertilizer, and it may be good for 3 days, or 5 days, or 2 months. And so the process is, how do we increase the efficiency to help you get the value out of that fertilizer? Because all they are is chemical compounds, and they can be manipulated. So the fertilizer companies won't do that. It's not in their best interest to make a fertilizer last for 4 months or 5 months through the growing season. They would much rather have you buy an additional truckload or 2. All right? So as we look at this, everything that we're trying to tackle here, we've created and put together to solve a problem. And what we find is over and over and over, we have soil problems, we have plant growth problems. So this is all first-hand, let's fix a problem kind of approach here. We'll talk about the minerals, the microbes, the enzymes. All of this stuff works together. You can't separate any of these things in agriculture. If you're going to get this working right to where the soils are functional, the microbes are there, the plants can take up the nutrients and grow, it's all got to work together. When we talk about our mineral management, we're not going to go into a lot of chemistry here, but Jim talked briefly here about the minerals that make up the structural components of a plant. Dominantly, 99.5% come from these minerals right here. So, but down here we've got another group of our trace elements. They're not adding to the structure. These trace elements are the cofactors to the enzymes that make the enzymes work. And we're going to talk about enzymes a little bit later on here, but I can't over-express the need to have your enzymes functioning. Because every living system, whether it's a single-celled microbe or 100 trillion-celled human, every process is activated and run by an enzyme. And these enzymes, we don't take a breath, we don't blink an eye, You cannot move a muscle, and you cannot process a single thought without it being enzymatic driven. Period. These enzymes run every function of life. But these enzymes either function or they don't function depending on the activators. The activators are dominantly your minerals, and they're your trace minerals. Now, potassium that we know of right now activates about 387 enzymes. Magnesium, it operates maybe up to 50 enzymes that we know about. Come down here, look at zinc, approaching 400 different enzymes that we know about so far. Calcium is an enzyme activator. Phosphate is an enzyme activator. Dominantly, that's the job of this group. So when you start coming down into here, if you want living systems to function, you have to have minerals. When you look at the pecking order of these activators, your trace elements come first. When you look at a vitamin, it has to get put together. An enzyme has to take this component and this component and this component and make a vitamin out of it. Can't do it without these trace element activators. So, these are the systems that we want functioning. When we look at a periodic table of elements, conventional agriculture will tell you there are 17 essential nutrients. These are the ones that plants really don't function without. All right? So you've got positive, you've got negative, and then they've got a little group called the beneficial guys. They kind of aren't really quite essential, but they're really kind of helping push the wagon down the road. Well, you've got a lot more than that. You have a tremendous amount of minerals that play roles that we don't know. The USDA quit doing great research decades ago. And so they'll tell you there's 17 essential minerals. I'm going to tell you there's probably close to 70 or 75 very essential minerals. They will add to the plant's ability to function. And so we want to talk about the positive and the negatives. What happens in soil chemistry? Why do we lose our fertilizer? Why does soil stick around? And what makes it soluble, what makes it not soluble? So we're going to talk a little bit about this bonding as we go through here. But just realize that everything in nature plays a role. If we understand what it is, we can use it to our advantage. Because this is how it all works. There's a reason why a guy can get 400 bushel corn and a guy gets 200 bushel corn. You can go back, dig down through the soil and the plant, and you can look at the application and you can start to pinpoint the problem. So it all becomes down, how do we manage these resources? Okay, when you start about the positive and the negative thing, okay, one of the very first easiest ones, we take a little bit of hydrogen, we take a little bit of oxygen, and what do we get? Everybody likes water. It works really well. All right, we take a little nitrogen, put a little oxygen with it, we get a nitrate, we get ammonium. These positive negatives form these different bondings. And so when we look at fertilizer toxicity, when we get these mineral elements in here, we need to be concerned about what the pH is, what tissues or what minerals, when we bond these things up, are toxic to the plant. Are they going to burn the tissue or are they going to dissolve the tissue? So we want to look at those things. You have very low pH products, very high pH products. You have some that are more neutral. And this has to do with their ability to stay soluble. Phosphoric acid, when it hits a high calcium soil, the reaction time is about 15 seconds. Now, you have to have a pretty quick plant to get dense. And so, in lower calcium soils, your phosphoric acid at 2 pH is going to hang around a little bit longer. But it's not going to hang around very long because Mother Nature says, if I'm trying to keep my soil in a balance of 6 to 7 pH range, and I throw in a 2, nature's going to fix it very quickly. When we start looking at our soil complexes, your cation exchange capacity is really just your holding tank. How many negatives that are coming from my organic matter, my humus, and my clay can hold how many positives? That's all it is. It's simply negatives holding on to positives. The higher my capacity to hold on my negative side, the more I can hold on my positive side. Sandy soils, they don't hold much. The CEC on those guys is 1 to 5. Okay? When we get up into your heavy clay soils, a lot of organic matter. Darren, you got some buggers up there pushing 50. Okay? That is a beast. All right? You could train load stuff into that soil forever, and it'd hold it. And so he's got this tremendous reservoir of holding capacity. But they present their own challenges in dealing with them. Okay? Our starters. As we look at this, as we talked about this, any of the minerals we put in our starters are going to, when we buy them, they will be soluble. Okay? They're in liquid form, they can be in dry form, but they have ability to solubilize. The second they hit or are introduced to 75 or 80 or 85 other soil minerals, the equation starts to change. And this is the problem, is what you buy has been chelated enough by the manufacturer so that your nitrogen stays away from your phosphorus, and maybe your potassium stays away from your other minerals. So you've got a few chelators in there to keep it in solution. They didn't fix it for the other 80 that are out there. So as soon as we put that starter in the soil, all of these other minerals start to have a say in what happens to that availability. Okay, that's called inefficiency. We don't want to lose that because we intended that nutrient to go into a plant. And if my soil takes it away earlier, I simply have lost that money that I've spent. Jim, where's your roll of money? I want to give some of it away. Come on, Jim. You chicken. You see that big roll of money he's got? I'm going to try and give some of it away here in a minute.
Usually I owe you.
Corey, go get Jim's roll of money. I need his money. Anyway, the fertilizer companies have kind of got us trained, and we're going to talk about that. What we do, again, as I mentioned in the brewing room, is our job isn't to sell NPK. You're going to buy your fertilizers from your co-op. We just want to make some better choices in how we handle it. So what we do on our phosphate side, how we deal with this, is our phosphate is, oops, got to come back. Our phosphate is very, very negatively charged, very reactive. Okay? We are going to take some biosurfactants and some amino acid bases, and we are going to attach it to that phosphate molecule. So we're going to put these positives on this negative, and we bring the charge to 0. So when the phosphate hits the soil, it has no attraction to a positive or a negative. It'll sit there and sit there and sit there in solution. We do the same thing with our potassium. Is we don't want our potassium tying up with our phosphate. We don't want to lose it to our sulfur, because those are negatively charged particles. So before we put our potassium in the soil, we're going to put on some organic compounds which have a negative charge. And we're going to take the charge on our potassium to neutral. And we can take the salts that are in these fertilizers. When you have an NPK starter or a side dress, you're going to have salts. We are going to take the organic compounds and chelate those salts so they are not going to affect your germination or your roots. Now, one of the things that we do is, out in Idaho, we grow, Jim, you got your bucks?
Yeah.
I need a roll of money.
Well, I tell you what, you're lucky because I just printed all these up this morning.
I only need, I just need $10. $10. Oh, this is good. Good. All right. 10 very fresh, off the press dollars right here. Okay. Now I'm gonna offer a trade here. This is good money. Good money. Now, who is going to help me out here? I need $100 for this $10. Now, come on, help me out. This is not working, guys. Come on. Marlo, will you give me $100 for Jim's $10?
You gotta tell me what I have to know.
Nothing. The less you know, the better.
That's dangerous. You just went the wrong direction.
Okay.
You're working for the co-op.
There you go. Okay. This is the exchange the fertilizer companies want us to take. We give them 100, we get to put $10 into our plant. That is not a very good exchange. And so we want to try to change that equation, and this is how we do it. You can't lose your fertilizers when they hit the soil. And so there's a process of dealing with these mineral elements that allow us to manipulate this in a completely non-toxic way. All right? In Idaho, we have the state sugar beet record for the last 3 years running because we keep breaking our own record. And what we found was beets are very sensitive. And we were up talking to one of our growers a couple of years ago, and he said, 1034, he says, I put 15 gallons of 1034 in with my beet seed. And Salam, who makes the bio-release and the Soluplex, went ballistic. He said, you're crazy. He says, there's way too much salt. And the guy said, no, I put in 1 gallon of bio-release with my 15 gallons of 1034. And he said, those beets come popping out of the ground like crazy. And Salam realized that what was happening was the organic compounds were completely taking the salt factor out of the equation. Now, for those of you who grow sugar beets or don't know much about them, 4 to 5 gallons of any starter is maximum. 10 gallons is suicide, and you're nuts at 15 gallons because of the salt factor. But if you can take the salt factor out, you can get the nutrients into a form that the plant can use without the toxicity. And so when we push out 45, 47, 48 ton of sugar beets to the acre, we've simply created a better, longer mineral availability for that plant to grow. We got a cranking good start, and we didn't have the toxicity. Yes?
On the sugar beets, you wouldn't have to know what the sugar content was.
Yeah, I absolutely do know what that is. Some of those fields will push above 20. So we didn't crank the volume up to tank the sugar. If you manage your minerals right, you won't do that. Because what you will see, exactly as you had suspicion of, is, man, if I crank up that kind of volume, I've got sugars in the low teens. That's not what they want when they buy sugar beets. Okay, we also we grow about 15% of the state's potatoes. And so this is what we do with potatoes. We will put in 1/4 to 1/2 of the phosphate of the other growers. Now keep in mind, the state of Idaho's average production on 300,000 acres is about 300 sacks to the acre of potatoes. We will put in way less phosphate, way less nitrogen, and our growers, depending upon how aggressively they manage, will grow between 400 and 600 sacks per acre on less fertilizer. And it's not that we're spending more money, it's that we manage our fertilizer differently. And we're not doing this on a few acres. We're doing it with some of the largest producers. Our largest farm in Idaho is 70,000 acres. So this is not a small scale. And when you have potatoes, you can only grow potatoes once every 3 years. So you're growing grain and other rotational crops in the process. So these products are made in one place. They're about 8 to 9 years old, and they're specialty products. We're going to try to manage these fertilizers way different. So we've got some time, and we've got a lot of experience behind us in doing this. So let's move on. Side dressing. When we put out nutrients for a plant, we want to hit the plant timing just right. The really fascinating part about all these plants is they have these diets. They're like us. They want to be fed way more often than once or twice a year. How would we function if we got dinner at Thanksgiving and we got dinner at Easter? That's about how we fertilize. We put a little stuff out in the fall, we come back and about Easter we put a little bit more out. Pretty rough diet if we're going to be out there working every day. Well, these plants don't live that way. So if we put something out that ties up, or it's not available at the right time, our plants are simply not going to respond. So when we look at a plant growth uptake, when I did this research and put this together, what I realized is these minerals are all coming into these plants at different amounts at different times. Potassium on corn, week 6 and 7, is a major spike. And when you look at the sulfur uptake, it's completely backward of your other nutrients. 90% of your sulfur is coming in after tassel, 10% before. Your plant isn't looking for this stuff anywhere near close to the same time. When you look at your 4 major nutrients in corn, nitrogen first, potassium is right behind it. Then you look at phosphate, and sulfur is this far behind phosphate. On a 2, yes, fire away.
Which way would you approach your corn to get your potassium in early?
On one of these spikes,
Products and timing to do that.
you can use a liquid potassium sulfate. Is a great product to do this with. We're going to talk about this plant nutrient timing a little bit more. This one is just as we talk about side dressing, the timing of fertilizer is really quite crucial to this process. To try to solubilize and keep all my potassium up here so I can manage 2 spike weeks when I really only need it to go through this through the season, it's way more efficient to use a little bit of liquid right here than try to bring a dry program all the way up through here for the whole year. It's very much more cost effective to switch to some of these liquids when we side dress. And if we chelate it, we won't use them. Yes, wait.
So then your sulfur, you just spray over top. If you can't side dress on at the same time, so is it more effective in the ground or spray over top?
It depends on the product that you're using. If you're going to put out like some ammonium sulfate, you're going to have it on 6 weeks before you want your material to release. The problem is you're going to be releasing your ammonium back here when you're releasing your sulfur, and your plant isn't going to use much of your ammonium at that point.
So that's like an ammonium thiosulfate liquid? You have it down 6 weeks before the spike?
No, if you're on the liquid, you can put it in a week before, right here as a side dress, and chelate it and keep it in there.
For the sulfur too, or just put that?
The sulfur will hang up too. Yep. We can hang on to both the positive and the negatives, and we want to keep it in this soil so that it's available down here.
But if it was dry ammonium sulfate, you would recommend putting it in?
You have to have it at least 6 weeks ahead of when you want it dissolving. Potassium sulfate. I've got alfalfa farmers, they'll put it on, and you won't see a peep out of that for at least 4 weeks. And then all of a sudden, between 4 and 6 weeks, things start to take right off. So you've got to have these you've got to anticipate on dry a breakdown period. On liquids, if you put it in, you're within a week of getting it in, getting it down, and starting having it come back up to the plant. So again, you want to try to manage these peak weeks here with what your fertilizer program is. Yeah, William.
So you can put your sulfur in with your PDK, your side dress, or you can come back with your sulfur when you need it, like a week before the peak.
Well, no, your sulfur is going to come in down here, but we can put it in back here and hold it. Okay? The thing is, if you're going to put on a dry, you've got to have lots of lead time. If you're going to put it in liquid, you can't lose it. So we just plan for it either way. Richard?
Foliar feeding, does that make sense?
It does. But the problem with foliar feeding is you have a limitation to what you can push through the leaf at any one time. You can only get about, maybe, depending on your mineral blend, not more than 3 to 4 pounds of uptake of all of your minerals per acre at one given time. And so you can't load up 30 pounds of potassium through the leaf. The majority of this has to come through your root system, guys.
Will you take ionic materials, like ammonium sulfate?
If you can dissolve it.
No, say it's
Yeah,
it
will.
It's a solution. It will transport through the core of the leaf.
If the size is right. We're going to talk about this. This is a very good question. On your foliars, okay, we'll take a second and just talk about this right here. All right, plants have leaf surface membranes. It's just like our skin. There's certain things that will go through our skin. And I see this young lady down there putting on lotion. Do you expect that to go through your skin and get absorbed? It does. Okay, you can put lots of things through your skin. It doesn't have petroleum in it? Smart girl. All right. The thing is you have to realize that these surface membranes have limitations. When you're trying to put something through a root system or through the leaf, it's like a screen. Just visualize a screen door. You have to be able to get it to penetrate through the openings. There's a reason that basketballs do not go through screen doors. They're simply bigger than the holes. Leaf surfaces and root systems work the same way. Too big of particles can't fit through the opening. Okay? And so when we start talking about foliars, and we will talk about this, there's a correct way to make them and there's an incorrect way to make them. Most companies make them incorrect because it's cheaper. We put more time and more material in to build them differently. And so we're going to talk about this specifically. But yes, you can get lots of different types of minerals through your leaf if it's small enough. That stuff we're brewing in there, we can pass 75 minerals through the leaf system. So, Richard.
So what about the ammonium sulfate? Say when you work it, like in the spring, before you plant, you spread it and work them. Say it keeps your ground cooler and warmer. And so, but then you put the sulfate on maybe right?
Say that?
Then your sulfate was in it is not being used on where you want it to be.
Well, the plant's not coming after it. The thing is if I put something out and it's got to stay there for 2 or 3 months before my plant calls for it, how do I not lose it? I mean, I have a choice. When my corn is up here, when it's asking for the sulfur, I can't get out in my field. I've got 10, maybe 12-foot tall corn. And I don't have any equipment to get out there and broadcast anything. So I'm going to have to manage my sulfur in a way that I can put it down and hang on to it and not have it leach. And again, what we're looking at doing is managing spike weeks here. We have a base in our soil. We have some. But if we're going to really start to manage these yields, we have to start managing these peak weeks. Marlo.
Very good, there's your microbes. They will hold it, and they'll hold it in a form that the plant can use it when it comes after, whatever that is. Yeah, a good way to look at it is you get what you pay for, most of the time. If you use a high quality product, that will become with microbes. You got to have an air to break it down. Then the plant has the ability to use it when it needs it. Take your plant, cut it off down there, you cut it down, you start looking at your nodes. Okay? Most of you guys are going to say, wow, man, I got these nice bracelets. Look here, I got bracelets up here 3 nodes high, maybe more. Why is that plant shooting bracelets 3 foot high? Or I mean 3 nodes high? It's because if you cut that node open, you'll see it looks just like a cigarette filter, and it'll be all plugged up. And that plant is starving. So it sets out another set of bracelets, but actually those are nodals. Those nodals are going out after more food.
Yeah.
So if you were going to put down, like say 200 pounds of dry ammonium sulfate, because I already got that locked in for this spring, would you want to split apply that, put 100 pounds down pre-plant, and then side dress 100 when it's knee-high?
You could do that. We're going to talk about split application of fertilizers. Again, plants are like us. We don't like getting fed once every month or so. We like it kind of 3 times a day. You know, and if you're really working hard, 4 times a day is kind of cool too. But the point is every one of these plants have a unique diet. They all have a different personality. And if we understand what they want, when they want it, then we can manage our applications way more efficiently and way more timely. Saves us a lot of money, guys. I mean, when you start looking at what you can save here by just nutrient timing and selecting the best product for your fertilizer, you can save a lot of money. You don't have to overload on the materials to try to get this plant growing. Foliar. Let's talk about this thing right here that we talked about. Again, molecular size to get through a surface on a plant is typically 600 to 700 atoms in size. That's 600 to 700 hydrogen atoms stacked side to side. And I get bigger than that, it's just stuff isn't going to go through well. Now, so I've got to have very, very tiny compounds. Let me just give you an example. How many have used humic acid? Okay? It's a fairly common thing. Doesn't go well in a foliar because the molecular size of humic acid ranges from 8,000 to 50,000. So before I ever put it out, I have a size problem. How is an 8,000 or a 20,000 going to go through a 700 size hole? Basketballs and screen doors again. The next problem is humic acid is very, very negatively charged. Most of my trace elements that I'm putting out are positive. So I have this big black basketball sucking up all of my trace elements, and then nothing's going through the plant. So that humic acid molecule will sit up there and stay on that leaf surface until it's washed off. Then the microbes will eventually tear it apart and make tiny things out of it. And some year it'll see the inside of the plant, maybe. But it's a very, very ineffective approach so that we want to deal with molecular size. The other one is these minerals. Oftentimes in most foliars, if you look, they'll put in 4 or 5, maybe 6 trace elements, and they have 1 chelator. Very common, cheap one is glucoheptanate. It's a sugar-based chelator. Well, because every mineral has a different molecular structure, that 1 chelator is going to go find one of those minerals it likes better than the rest. So it's going to chelate one well, the other 4, 5, or 6 not so well. So they're going to start pumping up in size. When Salam builds a foliar product, if we put in 8 minerals, we have 8 separate chelators, 1 for every single mineral. Because we do not want anybody going on in our chelator, in our foliars. We don't want them hooking up because it doesn't take many hookups to get past this size right here. Now, I will tell you the molecular size of biorelease and soluplex is down in the 200 range. It is very tiny, very highly charged, very active particle with both positive and negative charges. And that's why it will release, and it will release both positive charges in the soil, it will release both negative charges in the soil. We'll talk about that. But you have to pay attention. Size matters here, guys. It needs to be really tiny.
So will a surfactant help enhance that into the membrane?
Not if it can't restructure the molecular size. A surfactant it breaks surface tension. That's what they're really designed to do. And so if you can reduce the surface tension down to less than this, it'll work. But oftentimes the surfactant won't do that when you have oppositely charged minerals. Okay? Let's see, let's go on to the next one. Timing, or your foliar timing, corn, soybeans, and wheat. All right, as we look at this, your plants go through these really cool growth stages. And so we want to put these trace elements or these nutrients through the leaf just before these plants go through this big push that helps determine yield. On corn, right here at V12 to V16, V17, what is going on? Jim, I'm going to give some of your money away. William. Okay, length of your cob and the rows, number of kernels going down. It initiates it at V12, it closes it at V17. You don't have any longer than 2 weeks here. When is it initiating, when is the plant initiating the rows around the cob? At what growth stage? V3. V3. How long before it gets to V5? How many days between V3 and V5?
7 days.
Okay. You have about a week. And so that window is closed. So when a guy gets 14 rows, 18 rows, 24 rows, the plant simply said, I have enough nutrient to express this type of yield. What have I got that's making me function? So when we know that these crucial growth stages are coming right through these things, we can actually assist the plant in helping build yield. All right? Let's go into our microbes. Every one of your plants have this crucial growth stage. Your soybeans, your wheat, your alfalfa, your corn, your canola, your cotton, they all have these different personalities. And so we can sit down with you and say, look, these are the minerals that function these things in your plant. If your soil doesn't have them, we need to look at applying them. And so it comes back to driving these plants to enable them what they're designed to do. When we really look at these plants, they're absolutely incredibly brilliant. They have a DNA package second to none. We don't need genetic modification to improve plant growth. We need mineralization and nutrient availability to operate that system that comes with them. The DNA is there, the enzyme package is there. We just have to turn it on with the building block minerals and the trace elements to really fire up that system. And it's about getting them there at the right time. Microbes play a crucial role in this whole process of taking something that's dirt and turning it into a plant-available compound. Nature holds things in insoluble form. And the plant has a big struggle taking stuff from this form into the squash that Gardner Dave just fed us. This is a struggle. And so all of these inorganic compounds have got to get transformed. There's nothing better on this planet to do it than a microbe. Those little guys are absolutely brilliant, and they know what to do and they know how to do it. Our smartest chemist isn't remotely close to the dumbest microbe on this planet. And so let's use these guys because they can be a huge transformational force to take these insoluble solids or gases and put them into compounds that these plants know they can use. You have to remember, there's a tremendous amount of communication that goes on between soils and plants and microbes. We think this is all dead, benign stuff out there. Not even. This system out there of communication is second to none in the world. If you think we got smart bombs, came from insect communication. Everything we've learned has come from nature. So when you start talking about plants alter their sugars to feed specific microbes on their leaves and in their root systems to go get the minerals for them, you can't tell me this is an accident. It is so perfectly orchestrated that that system is flawless if we'll learn how to use it. Plants do this. When you take and go through a microbial growth cycle with the plant's turning these microbes on and the plant's turning them off. And so they're working in complete harmony if they're there to do it. Now the problem that we've got is we've used a lot of stuff in our soils that we've nuked these poor microbes. And so the plant is putting out exudates to attempt to feed the biology, and what's there? Pathogens. We've got fusarium, we've got pythium, we've got rhizoctonia, we've got Gossa's wilt. And so if the good guys aren't in that root zone to help feed the plant and provide that defense mechanism against the pathogens, pathogens just walk right in, loot the bank, take the money, kiss the girl, and off they go. And they get off with all the goodies. They're going to take the root exudates and eat them and grow to huge numbers, and then they attack the plant and kill it. Sudden death syndrome in soybeans, fusarium. The fusarium is being fed by the plant. Those exudates were not intended to feed fusarium. It's intended to feed all the good guys. All right? But absent that, these microbes, they're not there, they can't help us. Microbes make this really cool thing of they restructure all these electrostatic bonds. They'll take the calcium away from that phosphate. That beautiful purple-orange thing you saw, or that pink and red and purple thing, calcium phosphate come out of that lagoon. Microbe will take that apart, make it plant available. Okay? They put things together and they pull things apart. When we want to grow plants, microbes will help in that process. When we want to take the plant residue apart at the end of the year, microbes are the guys that do this. And if it weren't for the microbes, we have about 30 days and we drown in our own waste. Simple as that. They get rid of this stuff and reprocess it. Microbes produce the enzymes that produce a lot of biochemical reactions. And so these guys are indispensable. They're going to put things together, they're going to take things apart. And Jim talked about this, we'll just go through it quickly, but this is the tear-down cycle and the build-up cycle. It is all run by enzymes and microbes, guys. If you want this functioning, these little guys, when you get them out in your soil, are so functional, they're cheap, it's way better than fertilizer. But we've got to put in some management practice so we don't take them out. Biology, on your plant leaf surfaces, you should have what looks like New York City on your plant leaf. You should have a huge colonization of microbes on there. You should have this huge colonization of microbes all the way around your root system. So the biology functions above the ground, functions below the ground. Right? Let's see. We've already talked about this. They decompose the plant matter, the nitrogen, the minerals, they make that accessible, oxidization, transformation. We don't put out very many minerals that we buy. We go to the co-op and they bring out the truck. Very darn little of that is in plant available form. Take phosphate. The most common form of phosphate that we buy, P2O5. You look on your fertilizer bag. P2O5. Your plant can't use that form of phosphate in 1 billion years. Has to get fixed by a microbe. It's going to become H2PO4 or HPO4. The microbes have to go in there and say, yeah, man, I'm going to take a little hydrogen. I got a little bit of oxygen over here. I'm going to move around. I'm going to push this one around. You know what? Now, I got something the plant likes. But before, that plant goes, I ain't touching that stuff. pH is wrong, the mineral structure is wrong, and the plant can't take it in and fix it. Can't happen. So we got this microbe that says, you know what, I know how to fix this problem. So lots and lots and lots and lots of those minerals out there that are sitting in this clump are going to have to get fixed because you're not buying them in the right form. Okay? So these guys are pretty indispensable. Microbes are going to change the soil structure. That's the cool thing about these guys. You want to get rid of compaction, you will never do it without microbes. You can rip your soil from sun up to sundown, and as soon as you get water going back in it, the electromagnetic bonding, positive and negative, is going to set this thing up like concrete again. You want to change it, get those cute little microbes down there. They will kick butt on that soil structure. When we talk about soil structure, there's only two things you got to remember. I either got cannonballs, which is this cloud, or I got popcorn balls. Now what's the difference? There's lots of little pores and air spaces in my popcorn balls. And I got all kinds of cool things going on down there. I got microbe condos, I got air and water, and I got my fungi and my protozoa moving around down there, and I got my nematodes, and these are good guys. They're over there eating the fungi. They're over there killing the bad guys. So you've got this whole colony of things that can happen in popcorn balls. You got nothing going on in cannonballs. All right? This whole soil thing has this cool thing. It's where this guy gets eaten by this guy, and then these guys get eaten by these guys, and these guys come over here and eat these guys, and these guys eat these guys. We think about big fish in the ocean eating the little fish. Same thing's going on in the soil. So there's this whole life system down there that plays all of these really cool roles. And I will tell you that bacteria does not do the same thing as fungi. And fungi does not do the same thing as protozoa. And the protozoa aren't doing what the nematodes are doing. And the macro and the microorthopods all have a different role. And your earthworms and your shredders, all the way on up, just keep playing a different role in all of this wonderful life that we don't ever see. We're going to do some brewing in there. We hope that within 3 hours we activate some microbes so we can look at under the microscope back there. But life in the soil is absolutely fascinating.
What fraction of the beneficial microbes survive over winters for the following year?
Lots of them, if we don't kill them. This is the nice thing about microbes. Microbes can be pretty perpetual. You look at, especially on perennial plants, you look at some of these trees. Where's the fertilizer trucks out in the forest? Ain't any. You know, plants say, you know, I don't quite need that stuff. These microbes, especially your perennial type microbes, your fungi and your bacteria, your actinomyces will hook onto these root systems, especially your symbiotic ones. They will last, they will live for hundreds of years. When the plant goes dormant, they go dormant. When the plant's active, they're active. They're getting fed by the plant. The cool thing about photosynthesis is the plant takes all the sunlight energy, puts in water and makes sugars, and it forms all these mineral compounds. You realize that anywhere from 25 to some plants, 60% of that is going out of the root system. And it isn't because the plant says, hey, I just got too much, I just made too much. I'm going to share with the soil. It's feeding the microbes. So these plants are designed to activate and drive their biology to do very specific functions for that plant. And so it's pathogenic defense. It's all kinds of cool things that are going on down there. And so when we learn how to utilize these guys and what their role is, we can really get a lot of free stuff. I mean, this is like the fertilizer company for free, if we know how to use this. And we're going to talk about this. Okay? Bacteria. We're going to do microbe math here. And this is how minerals get produced in the soil. Now, we don't want our fertilizer that we apply to get lost. So one way nature says, how I'm going to hold nitrogen or phosphate or potassium is, I can put it into an insoluble form. Plant can't get it. Or I can stick it into a microbe. Now, this microbe, he's going to kind of hang on to that soil. He's going to build a little community. So when the water comes through, they don't wash out. He's going to hold lots and lots and lots of minerals. So you have two types of microbes generally. You have those that hook up with the plant, they get married, they hook into the root system, and they're symbiotic. And then you have the other guys that are kind of in that group where they're called mutualists. They don't get married, but they just kind of live together. Okay? They're still kind of helping each other out. And then you've got the really stingy farts. Okay? They have no intention on sharing one thing that they eat with the plant. Ain't happening. Every speck of nitrogen they can get, they're going to keep. They ain't giving it up. So what nature says, all right, for you stingy guys that don't know how to share, I'm going to have this protozoa come eat you. You are now my lunch. So how this works is, bacteria are the most dense organism on this planet for nutrients and minerals. They hold 5 carbons to 1 nitrogen. But it isn't just nitrogen, it's phosphate, it's calcium, it's potassium, magnesium, sulfur, manganese, iron, zinc, boron, it's everything. These microbes have all these minerals inside of them. Now, the big guy comes along and says, I'm going to teach you how to share. So, his carbon to nitrogen ratio is 30 to 1. You and I are 30 carbons to 1 nitrogen. So, for me to get my 30 carbons, I got to come eat, if I've got 5 to 1 and I'm 30 to 1, I got to come over here and eat 6 bacteria. So, I like bacteria, I gobble up 6 of the little buggers. Now, I also have 6 nitrogen. I can't keep 6 nitrogen. I can only keep 1. My balance is 30 to 1. I can't have 30 to 6. So, like anything else, I simply excrete what I don't want. So, when I put this out, I'm putting out 5 units of nitrogen. It comes out as NH from the soil, and the plant says, thank you very much. I get to eat too. So, these protozoa eat tens of thousands of these guys a day. Because these guys are big, hungry guys with a very active metabolism, and these are little, tiny guys. So these guys are eating and pooping, and there's this plant food laying around. This is how nature turns these minerals back into a plant-soluble form. The next thing is your nematodes come over here and they primarily eat your fungi. Now you've got, Jim mentioned, 95% of our biology out there is great stuff. They're there to help us. 5% are pathogenic. So we've got nematodes the good nematodes eat the bad nematodes. We have fungi that trap nematodes and they eat them. All right, so you've got all of this stuff going on in the soil, but it's the same process. Nematode eat a fungi. He's got 100 to 5 now. Got to get rid of 4 nitrogen, 4 calcium, 4 potassium. and the cycle continues to go. So when you look out on the forest, you go, gee, I wonder where the fertilizer truck tracks are. You don't have to wonder. The fertilizer trucks are underneath the ground in the form of these microbes, eating each other, releasing the nutrients so that the plants take it up. So it all works very, very wonderful together. So if we want to create our nitrogen in the soil, we've got to make sure we've got protozoa. And what I will tell you, because of the way we farm, we don't have much fungi and we don't have much protozoa. Not there. Most of our bacteria survive because they're pretty tolerant to what we do. But our higher organisms are not. Also, when it comes to crop residue, all right, bacteria aren't going to decompose things that aren't green. It's out of the carbon to nitrogen ratio. For example, why does a cedar shake last for 60 to 80 years on a house, or a cedar post last for 100 years in the soil? I'm giving away Jim's money you did. What is it? Pardon? You're going to get half of it. Keep going up. Keep going up. Keep going up. There you go. You just earned Jim's $5. Okay. Cedar, 1,000 carbons to 1 nitrogen. There are so few microbes that can eat it. That's why it's going to hang around for 100 years out in your soil. It's still there. Nothing can eat it. Why do you and I like potatoes? And why do we like a little steak once in a while, and a little fish, and a little apple, and banana, and even some of Dave's squash? Why do we like that? It's our carbon to nitrogen ratio. When you see a cow or a horse standing out in a field, and it won't eat the tall grass, but it'll eat the short stuff, what it's telling you is that carbon to nitrogen ratio of that grass has now got beyond the animals. They ain't going to touch it. It's going to go eat something that's short. When you look at the carbon to nitrogen ratio of short green grass, it's probably 10 carbons to 1 nitrogen. When you look at it, ready to go to seed, or to stand in this tall, it's 60 to 70 carbons to 1 nitrogen. When it's dead and yellow and senesced, it's 150 carbons to 1 nitrogen. Who wants to eat that stuff? I've really never found straw sap very delicious. It's not very delightful to eat. But I quite like Dave's squash. Okay? It seems to taste really good. It's in our carbon to nitrogen ratio. If we eat too much steak, we got too much protein, we simply excrete the difference. Okay? It goes out as a nutrient. So this is how all this stuff, this cool stuff works in the soil. When we use microorganisms, these guys can fix nitrogen for us. We can buy it synthetically, or we can produce it with microbes. There's lots of microbes that deal with nitrogen fixation, or making phosphorus available, or breaking down zinc, or solubilizing iron or manganese. These microbes play a really great role. If we learn how to use these microbes can dramatically reduce our fertilizer budgets. But we have to have an environment out where we're not killing them. If you put them out and then you spray, you're probably going to kill them. I have conventional growers that use all azotobacter for their corn and their wheat. They're not organic. They just simply say it's cheaper. It's way cheaper to use the microbes than to buy the urea or the 32% or the ammonium nitrate. It's just cheaper. So they've had to alter their practices so they don't kill them. Okay? Darren used a little bit of azotobacter last year. Okay? Mycorrhizal. This is another very crucial microorganism that will help a great deal. These microbes, especially when things get dry, play a huge role in the transformation of minerals to plant nutrients. And these mycorrhizal come onto our root systems, and what they do is they dramatically extend the root's capacity to gather nutrients. They drill right in. At first they're a parasite. The plant's got to feed them for a few months. But after that, they spread out like a cobweb through the soil, and they're solubilizing. And I will tell you that microbes have enzymes that are incredibly stronger than anything a plant can put out. When you look at mineral displacement through a plant, the plant's got to push out hydrogen to push something off of the clay colloid. Okay? All of your nutrients are held on the clay or organic matter. And so your plant says, oh, you know what? I got to put out one hydrogen to go push off the calcium. Well, let me tell you what this takes. Calcium has a molecular weight of 40. Kind of a heavy guy. And it's got a double charge. Hydrogen has a molecular weight of 1, and it's got a single charge. Now, I got this bully over there. Control up front. You can see the difference between this one and these guys right here. And especially on your perennials that are going to be out there for a while, it's a huge difference right here. Look at the difference in the two orchards. I work with the largest blackberry grower in the northern hemisphere. They're down in Gastonia, Arkansas. And you are absolutely nuts to put out a blueberry, a blackberry, or a grape without mycorrhizal on them. Now, some of on blueberries, they don't like most mycorrhizal. But your blackberries and your grapes, you will extend the life of your plant, and you will make all the difference in the world putting out a little bit of mycorrhizal. You can see the difference just in the growth and response rate. These fungi are going to gather nutrients that the plants can't get without them. And you can take any of the plants and you can see the difference in the root size and the plant growth by having this microorganism inoculated down there. Okay, when we go into our...
And we should point out, we have that in our catalog, the mycorrhizae. They can go into the starter.
Yeah.
And we also use it in our seed coating, our ProfitPros.
Okay. And
There's a question over here.
yeah.
Would this affect, I had a forester tell me that a couple of my oak trees were dying because of the drought.
Mm-hmm.
Would this help the oak trees better utilize the water that's there for them?
Absolutely. It's not just the water gathering capacity, but it's also the mineral gathering. When your trees get old, what happens is they've been in this place for a long time. And when you think about it, they're pulling lots of minerals from the soil and they're sticking them up in their structure. So over time, they're mining their own base. And as the tree continues to grow, you have a reduction of minerals and an expansion of the above ground tree. And in time, what nature says is, you know what, it's time to put all those minerals back in the soil, so you're going to run out of minerals down here, and you're going to get sick up here, and we're going to recycle this whole process. It may take 100 years or 400 years, or in the redwood case, it may take thousands of years, but it's always going to be returned and recycled. If you will take and put the minerals back into your root zone with the biology, you'll extend the life of your trees. Salam and I use this mineral tea in there and the biology to inject into the tree root system. We have a big tank and we have a diaphragm pump. We have this cute little soil gouger that goes around. We stick it down in there and boom, down goes the minerals and the microbes into these tree root systems. Man, these guys pop back like a scalded monkey. They're ready to come back and really get after life. But it's just because we remineralize their soil and we put the microbes down there. Now, one thing with your mycorrhizal fungi, it comes in a spore, which means it's all curled up in this cute little cocoon and it's resting. What activates it is the roots, the exudates from the roots. So you need this down right with your seed or on your seed. The problem about getting mycorrhizal fungi on a plant that's already established is getting it down into that root system. And you can do it somewhat successfully if you inject it down. But it's really tough to water it down and get it down in far enough. You kind of have to have a little bit of an injection system. But that's how you go fix this stuff. Get the microbes back down there and get some minerals with them. Anaerobic decomposition. Now everybody thinks these anaerobes are bad guys. And it's the same thing with aerobes. Only a small part of the aerobic population are really the bad guys. Just what happens is, when there's no good guys, the bad guys overpopulate. Nature doesn't have all of these weird voids out there. So, if we kill off all the good guys, and there's a food source out there, all the robbers and all the bad guys and all of those critters just simply take over the space. Well, it's the same with anaerobic decomposition. Realize 4 to 5 pounds of these wonderful little guys are in our gut, and they keep us alive. What we did, what are we having for lunch, Jim?
I don't know, I haven't looked on the menu.
Well, what I will tell you is lunch is just like this. Well, not quite literally, but figuratively. The steak and lobster that Jim is about to feed us, bless his heart, is not in a form we can use. So I have to have this wonderful little microbe take this steak and lobster and turn it into plant-based food. So what the job is in our gut is to take this, break it down, solubilize it, restructure it, so the villi in our intestinal tract come in and say, comes right through the cell wall, absorbs right into the bloodstream, runs it down this big long pipe full of cholesterol, stuffs it in the cell, and we go, ba-boom! It's working again. All right? So, did we decide what we're having for lunch?
Not yet.
Not yet.
I
Okay.
think we're having some of Dave's pork.
I think we're going to break this up and pass it around. Okay? But that's what these microbes do. They're going to tear stuff apart. That's what their job is. So if we take these beneficial anaerobes and we put them out in this lagoon, they'll take these solids and they'll start to liquefy them. Then we don't have to go out and buy a $500,000 aeration system. We don't have to dredge this puppy. We don't have to go out and try to deal with these solids. We can let the microbes do what they're designed to do. So that's a process for you guys that have hog manures and lagoons and cattle, is there's a way to let the microbes process this stuff very, very nicely. And when a microbe processes stuff, it puts it back into the right form. It's going to go out in your soil. And the other cool thing is, of this group of microbes that we use to decompose these hog and these cattle manure operations, they function as anaerobes down in the water. About half of that population switches over to be facultative. So when it hits the soil, these guys say, you know what, I'm going to turn my hat around, and I'm a good guy aerobe now. And I'm going to go out there and I'm going to kick butt on all those pathogens, and I'm going to fix this fertilizer or fix this mineral for this plant. And I continue to function in another role just as effectively aerobically as I did anaerobically. So these microbes are really, really cool guys. They can really do a great job for us. Anaerobic silage. Now, making silage for you dairy guys is an anaerobic process. And what we do is we use these microbes to help through the fermentation cycle. But the cool part is, this is a silage pit that's out in Utah. And this belongs to one of the agricultural professors at Utah State University who teaches dairy science. And I treat his silage because this was put up in October and we came and took pictures of this in March. What's missing on top of the silage pit? Mold. Mold! There's no mold on here. We lift up the tarp and this is beautiful. There's not one dark black or gray speck on one single flake of corn. Because the microbes that we put in here to help through the fermenting process, these food-grade, human food-grade microbes do not tolerate pathogens. Period. They won't let them grow. So if we want to control pathogens, it's all biological here, guys. Really cool system. So, and the cows like this stuff. They really do. And when these human food grade microorganisms get into the gut, they assist with the breakdown of this and the other feed materials that are going in. These are the same microbes that we use to ferment this, control the pathogens that are in the gut. So it's going to be completely functional in the pit, in the silage, in the animal, and you've already started to treat your manure.
And that's why it eliminates the pathogens in the manure pit.
Sure, absolutely. You control your environment with your biology. If you don't have the good guys in your soil, the bad guys will simply take over. It's the same with your manure. If we don't, we will go in, and our intent is to completely restructure the entire population of that lagoon or that pit. And we're going to put in the good guys that are very aggressive and very dominant to control that environment, because that's how we control decomposition and the mineral retention and get rid of the toxicity. David, or John.
In eastern Wisconsin, we've got, hundreds of salesmen running over top of each other to sell an additive to the corn silage and so forth to treat millions and millions of tons. The big issue, first the door opening or closing issue, is the cost per ton. What sort of cost per ton are you talking about with this product?
Jim gives this away. It's free.
That's going to change. That's going to change quickly.
This, David, let me just give you an idea. I treated a pit that was probably 60 yards long by 30 yards wide, and it was stacked as high as 15 feet. And I have no clue of the tonnage. They were into it less than $250.
That's giveaways.
Did you just spray that on the top, or did you treat it as it was piled?
No, what they did is we actually brought the equipment in. We have a tank with a diaphragm pump, and as we mix it with water and a carbon source, and as they bring in the layers, they simply take the wand and they just hit a light film on there, and all you do is just hit the layers. So 400 or 500 gallons of this treated this whole thing. All you've got to do is get a mist in the microbes. You got to remember, this green silage is coming in, whether you're using barley, whether you're using wheat, whether you're using alfalfa, whether you're using corn, it's chopped green. You've got 60, 70% moisture in this stuff. My goodness. And it's full of sugar. I mean, this is like lighting a match to gasoline. You hit these microbes on here, they take off, and man, they start to multiply, and they're in a perfect environment. It heats up, they've got sugar, they've got warmth, they got everything they need, and they start to ferment and do their thing, and they control the pathogens. And this stuff is not expensive. Richard?
Can I do it on the shoulder?
You can. I got guys that spray it as they chop it and put it in the whack. Absolutely. I got guys that spray the pits, and, you know, I got guys that spray the cows. I got guys that spray the cars.
Okay, we got guys like me that sprayed my corn stalks too this fall before I baled it. You can spray it right on before you bale, spray it with a field sprayer, and then windrow it up. And the beef cows like it.
Well, yeah. What the microbes are going to do is go in and start reducing this carbohydrate structure. This is going to be way better feed when you bale stuff. Absolutely. Put some microbes in there, controls the mold, starts the breakdown process, the nutrient transfer in the animal is going to be way higher.
Another thing that we want to try this year is we want to try putting these cultures in with our starter fertilizers or our side dress, because we think it'll go a long way to fight pathogens, like, you know, Fusarium, Rhizoctonia, Pythium, right?
Absolutely.
Yeah.
See, that's
very little cost. I mean, you're probably looking at what? A quart to a gallon?
Oh, 20 or 30,000 an acre. But it's not expensive, guys.
No, but as far as the quantity.
No, a couple of gallons of this an acre, 1 to 2 gallons an acre, the way this stuff goes after bacterial pathogens and fungal pathogens, I think 1 to 2 gallons an acre could really change the equation big time on Goss's Will and some of your fusarium.
The cost on a gallon, and what would that be?
About $1,000 for you, Doug.
We haven't really, Doug, really this coming year, we're in the test phase with it. So we're going to work with you we haven't really put a price on it. So we just want to get it out. So if anybody's interested, let us know.
It's not an expensive process.
No, it isn't at all.
This Goss's Will, when it comes in, sometimes it moves pretty quick.
And this will mix with the other stuff?
Yeah, you can mix this with mineral tea. You can mix it with your starters. You can mix it with lemonade.
Where's Rick at? Is Rick in the room here? Look at Rick!
Look at Rick!
Look at what it did to Rick's hair. No, Rick is. You're actually taking this culture yourself, aren't you?
Yes. I've been drinking up to 3 ounces a day, morning and night. The last week or two I haven't been because I've been out on the road too much.
But he no longer has any pathogens.
Don't stand behind me.
Well, a lot of these cultures we use are human food grade. Now, they come as human food grade. We're not telling you we have a food grade laboratory back there making it, but I have out in the West, I have this group of meat farmers, and so there's a co-op of 117 of these guys, and they of course are feeding the leftover parts of the rejected animals, which is your hog and your beef and your chicken, and of course they're full of glyphosate. So the organs that come in fresh, they get ground up, they get taken out in the mink ranch, and of course they're feeding it to the mink, and down go the mink. I've known this family for 30 years, and the mink used to get sick once to twice a year at the most. Now they're sick every month to every other month. And what's happening is the toxicity level has gone way up in their feed and the nutrient content has gone way down. So these mink have constantly got mastitis, they've got pneumonia, they've got diarrhea, and so the guy came to me and he says, we've tried everything in the co-op for 10 years, nothing works. And I said, well, take some of this stuff. He said, I'll just give you 5 gallons. And he said, well, I said, look, Cody, just take it. So he called me in 2 days and he goes, what is this stuff? I said, it's just microbes. It's food grade microbes. And he goes, man, he says, my mink are back to normal in 2 days. And I said, and so he kept trying it. And he called me up one afternoon and he said, do you think this would help my gut? And I said, it won't hurt you. And he goes, I know, I've been drinking it for a week. Because he washed his mink and he goes, that fixes them. Look at this. And I said, but you got to give up the Mountain Dew, Cody. You got to give up the Mountain Dew.
All right, Ken, this is going to be a good place to stop for lunch. And Larry showed me this article. As the nation grays like Ken, lower birth rate is a real red flag. The problem is that we're losing fertility in our population. We're not repopulating. And the real whole thing is who's going to pay all these taxes down the road and be the workers. So, I mean, we kind of been talking about this right here and why it's happening. And I bet you a lot of it goes back to how we're feeding our populations.
Well, when you look at the GMOs that are out there, you realize that these molecules are transferring from the food into the humans. And you realize that not only do I have the toxicity load from the glyphosate, but the glyphosate alters the internal biology. And when you change the biology in the gut, you also change the biology in the reproductive tract of females. All right? When you change pH in that tract, you're going to restrict fertility. The next thing is, glyphosate is very negative. Your manganese and your boron are your primary nutrients for setting seed and growing grain. They're the same minerals that are starting to set the fertility and the conception in humans. When you chelate those right out of existence, so they're not functional, how is that fertility process going to happen? It's not. I was with Dr. Huber in July at the Comfort Inn Motel. We were down for breakfast. He picks up USA Today, and it said, teen pregnancy down 36%. He looked at me and he says, do you think those little buggers are less promiscuous? I said, I don't think so. He said, they can't get pregnant. They can't get pregnant. It doesn't work. You look at the young people population in this country, 50% sterility. For every birth clinic we had 10 years ago, we got 14. So what's not working? Reproduction. And there's a reason why. You change the biology, you change the pH, you take the minerals away, that system cannot function.
Okay, just stay here a minute. I want to make one correction. I was wrong this morning, and I don't want to mislead anybody because I'm not in that, frame of mind or business. But Pam told me she's not a liberal, she's a progressive. Okay? And I just wanted everybody to know that. I'm sorry, Pam, that I made that statement. I just wasn't aware of that, okay? Okay, would you say prayer for us?
Yes.
I can't tell who got that right.
It's 4-0.
It's 4-0. Who said that? Huh? Oh, Chad. We got to get to Chad. Chad got it right.
Did he?
Yeah. He said 4-0.
Okay. You go this person. This guy's getting too much.
Yeah. What was the question? The question was, what is the percent or weight, I guess, of moly in a plant? What percent of the plant? What percent of the plant? Yeah.
Okay, we are back in the saddle.
We got 3 o'clock.
Okay.
But then, if we're going to run till 3 o'clock, and we're going to be doing some soil sample interactive here before that topic, and then if you want to stay around, any of you that run soil samples, we'll be willing to run those too.
Yeah, we'll do show and tell. We'll do some individual show and tell after. Anyways, we come back to our discussion. We want to talk a little bit about just the function of these enzymes. I know we've covered a fair amount of material, but the job of an enzyme is to take all of these substrates. Now these substrates can be individual elements or they can be compounds. And their job is to take these and make different products out of them. That's their job. They're going to put stuff together, they're going to take stuff apart. And so we really want the functional ability of these enzymes to work. And so, like for example, when we take a breath of air and we bring it into our lungs, it goes through a process of oxygen transfer, and in the process we make a product called hydrogen peroxide, H2O2. Well, our cells really aren't geared to deal with hydrogen peroxide. So for a split second, for just a split second, we have this hydrogen peroxide in contact with our cells. The enzyme that actually takes your hydrogen peroxide back to water and oxygen functions at the rate of about 60 million cycles a second. So these guys are like grease lightning. And so these enzymes have the ability to transform things extremely quickly so that we don't build up this toxicity. So when we're talking about literally increasing the rate of reaction by thousands to millions of times, these enzymes move very slow or not at all without activators. So these crucial trace elements, the vitamins, have to be there to get all of these different things functioning. And when things start to break down, whether it's a plant that just stops growing or a disease that starts to happen in a person, what it is, it's a red flag that something in that system is stopped. If we dig deep enough and we dig long enough, we can trace it back to a mineral deficiency. Some system isn't being supported. And these cells that work with these enzymes, they have three functions. You're either maintaining them, or you're repairing them, or you're replacing them. And this is all enzymatic driven. So if we want our plants to really grow, we have to utilize all of these trace minerals to fire up these enzymes to put all these things together. And so when we run out of manganese and we run out of boron, we quit setting grain, we quit producing seed. So if we don't get a good feel, we can go back and identify those minerals that are functioning the enzymes that are simply, we ran out of and that system stopped functioning. Let's see, Jim, we got this going. Oh, we got to warm it up. Let's see. Jim, how do we fire up this little varmint? Go get, what we got is money. We just need to get this little thing working again. We'll go this way. Again, enzymes work to put things together. And again, we can take three simple elements and we can start building all kinds of interesting things. DNA is simply carbon, hydrogen, oxygen. Our sugars, different structure, 12, 22, 11 is our carbohydrate or is our lactose. Amino acid, introduce just nitrogen into the equation. This is our protein structure. Our lipids, our fats and our oils, again, just carbon, hydrogen, oxygen, but they're put together in a different form. But this is what the job of the enzymes are doing. Dominantly, trace elements are the ones driving these guys. Again, to get a trace element is an element. It's by itself. You can't reduce it to any smaller form. But there's not a vitamin that's not a compound. Doesn't matter if it's fat soluble or water soluble. Doesn't matter where it is on the scale. They're all compounds. So something has to put those guys together. So in your pecking order, your trace elements will always come first. If you have vitamins present and no minerals, the system doesn't work. Got to have minerals there. So I spent quite a while on this vitamin, or on the mineral enzyme plant interaction. And can you get this fire up, Joe? Sure. See, these techie guys, they said they're so smart. Okay, I took the trace element and the enzyme that it functions, or that it drives, and you can go through and you can see what the different functions of these things are. You can connect the dots all the way through. Now I have 38 pages of this, and I want you to know that that is just the tip of the iceberg. Just the tip of the iceberg. But I wanted to make sure I wasn't off center on this, so I went through and did this. But molybdenum here, we're going to talk about that, because the big buzzword out there, as Jim talked about, is you have what they call nitrogen inhibitors, which is to slow the release of nitrogen down. We're going to try to stop it. Some of them work chemically, some of them work biologically. Well, when you look at the microorganisms in the soil that transfer the nitrate to a nitrite to an ammonia, or vice versa, back and forth, some of the inhibitors just kill the soil biology. Okay? That's one way to slow it down. I don't think it's a good way, but it's one way that the companies do it. The other guys do it chemically. They'll try to coat it, they'll try to do a slow release type reaction. But either way, and I'm not here to badmouth that process, but once you have nitrogen, if a plant takes it up and it can't use it, what good was speeding it up or slowing it down? Your nitrogen efficiency is going to come from molybdenum, so that when the plant takes up nitrogen, it can transform it. Because ultimately what happens when we take up an ammonium or a nitrate, it's going to go through a whole series of enzymatic processes to become an amino acid. And eventually, a whole bunch of more amino acids and enzyme processes, I end up with a protein over here. So, how many times do I have to change my nitrogen before it ends up as a protein? In some pathways, it could be dozens or hundreds. This guy right here runs that process. If you don't have high proteins, and we're building up nitrates in our plant, that means the plant takes it up in the nitrate form, and it says, gosh, I can't do anything with this. I don't have the equipment to take this any further. So the plant will go over, stick it in a vacuole, and it's like a little closet for the bad child. Okay, sticks it in the closet. Then when your animal eats it, what does that nitrate do? If you want to grow two things, you need lots of nitrate. First is bacteria, second one is weeds. Right? So when that nitrate hits that animal's gut, the bacteria go off the charts. Because you look at their carbon to nitrogen ratio, that's a huge food source for those guys. So they explode in population, the gut fills up, compresses the lungs, out goes the air, boom goes the animal. We just bloated it, okay? Or I produce so much gas that I can't vent it out the front door or out the back door. I get it with twisting bowel syndrome, kill my animal. This is high nitrate. What happened was my plant took up the nitrogen with water, couldn't process it. I didn't have the trace element, so my plant loaded up with nitrates and I'm killing my animals. Simple as that. So, this is a real crucial process that we have our trace elements there to do this. And so, we're going to show you some pictures of some really cool stuff we did with molybdenum. All right, nickel, zinc, we can go on and on and on. These trace elements run a lot of enzymatic systems. And these enzymatic systems are not just in plants, they're in animals, they're in humans. They're in microbes, they're in insects. Okay? So as we move through here, molybdenum is the trace element that we put with our nitrogen. And the ratio that we put it is, and this works very, very effectively. We've had guys use this for years, kicking butt on nitrogen applications. 2.5 gallons of 3% molybdenum per 1,000 gallons of 32%. You don't need very much, it's a very small ratio, but the molybdenum activates the nitrogen function in the plant, and it really goes to work.
So you put it on with the starter?
You put it on with your starters or your side dresses. We have some foliars that we'll build specifically for alfalfa richer. Well, we'll drop in a touch of molybdenum and just a touch of boron, along with the other minerals. We make sure that it's there. Alfalfa just goes like, holy cow, I'm in seventh heaven. But, Ken.
When you add this millennium to the 32%, how much increase of effectiveness is there? How much more nitrogen will be utilized?
Well, that's a tough question because your magnesium in your soil is going to come back and have a big say on that. And this is what we're going to talk about as we go through. But what we're seeing is some of these crops, some of these seeds, they have a pretty dramatic increase.
So we're saying that, say you're putting 80 pounds of nitrogen down to 32%, you add the molybdenum, you drop it down to 80 pounds of nitrogen.
Instead of what?
Instead of 100 pounds, if you add more.
I would say that's probably a safe guess. I would say it's a safe guess. Let us show you what we did with just a speck of this stuff, and then you guys can start to experiment. Now, we've only done this for about 3 years, so we don't have this endless reserve of data on here. You got to remember, Salam's company and my company were small companies, and we are heavy into R&D. When we make $1 off of something, about $1.25 goes back into R&D. We're broke all the time because we've got 100 more questions we're trying to solve. And so we do this stuff, we do all these experiments firsthand. And believe me, they're not all home runs. We think up of something that's really cool, it doesn't work. And then we think of something like that mineral tea in there that we brew up. I thought, you know, if I can move alfalfa 5 or 10%, I'll think I just hit a home run. Ha, ha, not even. That went out of the ballpark. And so some of these things we do a lot of experimenting with. And so when we try this stuff, when we're bringing it to you, we've already done it, we've already tried it, but we may not have all of this data on it because we haven't used it in every scenario yet. So, again, molybdenum goes with our nitrogen, our crops. Hey, we talked a little bit about this earlier. Your crops go through these very definite growth stages. And it's at these stages we want to activate the plant's ability to create yield and put this plant matter together. B3, our ear and leaf initiation. Right through here, we've done our ear. By B5, our number of rows of kernels around the cob are determined. This is set very early on. B12 to B13, we start to set our seed and kernel initiation. That's the length of our cob. And if I get 40, 50, or 60 rows down, there's a very specific reason why. The plant had the nutrients to start that genetic potential. When I have 35 rows, it's because my plant ran out of gas. Because your plant does not max out at 35 kernels down the cob. Richard?
So if you have to go up to 14 or 60 rows, you did a really poor job.
You can do better.
You did an average job.
What about the guy who's got 24? I had guys from South Dakota bring in 24 rows around. And I'm going, that's pretty bodacious. Okay? He's got things working the right direction. Now we just need to hit 60 long. Okay? Now we're talking some yield. But the plant's got the potential. It's just on the growing conditions, what's happening at B3 to B5? I can tell you, if you have cold, wet springs, soggy, wet soils, your calcium transfer is going to tank. Right? Your nutrient flow is going to be somewhat affected. This is where your biology comes in. If you're in a straight chemical system, you're going to suffer the worst. When you have the biology down there to take the highs and lows out of the soil temperature fluctuations and help transfer these nutrients, you're going to fare a lot better. Richard?
So, like, you know, for we from South Dakota, and of course, warmth in the spring could be an issue. Some of the guys, they meant that I think, you know, the snow is bad off the ground. I like to wait and make sure the ground is nice and ready, because a couple of years ago, the whole crop froze. When you plant to the V3, V5 is actually, you know, how long does it take to get to V3? That's 2 weeks.
It depends on, again, weather related. I've seen corn get planted and germinate in great conditions in 5 days. And it's here in 15 to 18 days after being planted.
So if you should we push and plant as early as we can, or just...
No, I mean, guys, your extra 1 or 2 days on the front end or the back end aren't going to make the difference. It's all the minerals in between that really make the difference. And the thing is you jump out too early and your plant is going to struggle through the cold temperatures and the soil and frost or whatever else you might have. I've seen guys, and I have farmers that will say, you know what, I'll plant a week later and I'll catch him in 2 weeks. And they do. They do. And so you try to just manage this the best that you can. There's a question over here.
So what is population? I mean, how does that affect anything?
Well, the population, you can overload the population for the mineral base, and then you really tank. I mean, a couple of years ago, we were invited back to Pioneer, and we talked to these guys about crop residue. A lot of these seed companies are now pushing out of the 30s, into the 40s, into the 50s. They can't they don't have the soils to support that kind of plant population density, and they don't even begin to have the microbes to digest the residue at 30,000 population, let alone 50. And the guy who's over 6 million acres in Illinois said, Ken, our biggest problem is crop residue. And I said, well, it goes back to the mineral side of things. One is, you don't have the minerals to support the microbes to even get rid of half of the residue you're trying to grow. And the next thing is how do you expect to grow double the population plant on the same soils if you can't manage your minerals? I mean, the red flags are already up, guys. If you can't have the mineral force to sustain a biology group to decompose the residue, how can you double the population and crank up the yield? Can't do it. And so, you know, these things go hand in hand. I mean, I know these guys want to push the plant populations and push the yields, and I'm not afraid of plant populations if you know how to manage the soluble minerals underneath them. Because once these plants run out of the first element, they shut her down. So I can have all the nitrogen and the phosphate there, and if I can't meet that potassium demand, I just clipped off 20, 30, 40, 50 bushel. Okay, I can do everything else great the rest of the season, but I put a cap on my yield already. So you have to be really conscious of this. I mean, you turn around and say, I'm going to take X number of bushel off of this field, I have to support that. And that's what we look at here with the crop nutrient calculator. We're going to deal with the crop nutrient removal factors. Okay? Because if a guy says, I'm going to grow 50,000 population or bust, you better gear it up. Because you'll have a wreck if you don't meet the demand. Okay.
But bringing your equation here, Ken, semi-flex versus fixed varieties, and in semi-flex, let's say that plant is lacking nutrient density during the growth stage, but then you get out there proliferate or something happens, will that compensate the hair length versus the flex one?
If we get it on in time. When you have a growth stage, is you have a window of time that the plant's starting and concluding. And if the nutrients aren't there through this stage, even if I apply them a week later or 2 weeks later, I can't go back and reset this biological clock to fix anything. And so this nutrient timing becomes an incredible important play in how I grow my plants. I don't necessarily need more minerals. What I just need them there is at the right time.
So in essence, if you miss that window, you're basically screwed because you're not going to get over that year.
You can't change it after that point. You have what you have. You know, people think that by tassel, I'm going to go in and change yield. There's only one possible way you can do that. That is, I can add more weight to my test weight. I can add more test weight. But I can't add more kernels. I can't go longer, and I can't go any more around. The plant won't reset that clock. So it becomes way more crucial on being ahead of the game to support that potential expression, because once you miss it, you're locked in. And the other crucial thing is if you put out a foliar and it does absolutely nothing, the take-home message was, I didn't have enough N, P, and K, calcium, sulfur, magnesium, to build the components that my trace elements activated the enzymes to do. If you don't have enough base minerals down, you're wasting your money on your foliars. They can't, there's nothing to work with. You gotta have them both. And so, if our NPK is lacking, don't even bother putting out trace elements, guys. You're not gonna make enough of a difference. You'll waste your money. But if you've got a good base program of your building block minerals and you fire it up with your trace elements, you'll get a nice response. Okay, as we come down here, we finish We finish all of our kernels at B17. At that point in time, the plant has locked it in, and that's what we're ultimately gonna get. What we can do is fill it, but we're not gonna add any more to it. Corn growth stages down here, silking. We're gonna go into black layer. Your final yield on your corn is the number of rows, the number of kernels, and your weight and your density of your grain. Okay, as we look at nutrient uptake on our corn, we look at these patterns right here. We've got some pretty peak weeks that are pretty critical. And we're taking up 57% of our nitrogen, 82% of our potassium is taken up by week 10, 58% of our phosphate. Right here, when I put this work together, I was really looking for the phosphate curve. Because phosphate is, unless you're a dairy farmer, where you got gazillions of gallons of manure to put out, phosphate's a problem for everybody. In the West, it's a big problem. Out here, it's a problem. So when I started this, I was going after the phosphate curve. The real sleeper here was the potassium uptake. Look how much potassium I'm taking up on this 300 bushel corn. I'm taking up of my potassium. I've got 21, almost 22% this week, 22% this week. I'm taking up over 44% of my potassium in 2 weeks. And for you guys who grow wheat, the potassium curve is almost identical to this. You're taking up a huge amount of your potassium when your plant isn't any taller than this. While your plant is prostrate out on the ground, before it ever hits stem elongation, all of your grains, it doesn't matter if you're talking barley, wheat, or oats, you're taking up potassium way early on in way high quantities. And if you miss that peak, you are going to clobber that yield. And so, daring you guys with 8% organic matter and 48 CECs, your potassium is a major problem. That, you have got Godzilla out there holding on to that potassium, fighting that plant for it. And it ain't coming loose. It's a real struggle. So if we're going to really push those grain yields, we've got to have that potassium early on. And I'll tell you on soybeans too, I'm right in the middle of soybeans, is your potassium's coming in darn early on soybeans too. It's coming in darn early on alfalfa, way earlier than we thought before we got into this research a few years ago. So it's timing on this stuff. So you can look, what we've done is we've taken corn right down to the week. Actually, when I did this, I did it over 130 days. I knew whatever was coming in every single day. But I put it into weeks so you guys wouldn't have to listen to me go through every single 130 days. But this is what happens. Weeks 1, 2, 3, and 4, there's hardly any nitrogen uptake. When you look at phosphate, goodness gracious, by week 4 after germination, I'm barely taking up 5 pounds. These plants, when they're very small, are not coming after this stuff. They can't use it. But when they start hitting their stride in here, they take off like a rocket. And this is what we need to do to work on our nutrient timing and our availability, because these 5 weeks are where we're losing our yields, guys. It's not your foundational minerals that you've got part of NP and K there. We're getting clipped off right here. Go ahead.
These weeks, is that emergent or?
After emergence. This is right after emergence, right here. Okay? Germination, when it comes up. So, we start the clock running from when she pops out of the ground.
Would it be flag leaf?
Pardon?
Flag leaf or before that?
On wheat?
No, on the corn when it first spikes out of the ground. On the corn.
Flag.
The flag leaf coming up the first.
Oh yeah, right here.
Yes.
Yeah, that's when we start the clock on, when we really want to start. I've seen corn, depending on springs, I've seen it out of the ground in less than a week, and I've seen it coming out of the ground in 3 to 4 weeks. So we don't really start this biological clock till we get her up and going.
What's the timing? between the application of potash and when it's available to the plant in the form to take up?
It depends on your form of material. If you're putting out a dry form, like, I don't like potassium chloride ever. I know it's cheap, and a lot of co-ops carry it because it is cheap. But you got to remember, when you start to surpass 80 to 90 pounds of sodium per acre, you start affecting your microbes. And so, what's the typical application of potassium chloride in the fall? Any hands? How much have you put out? What's the recommendation, Ken?
I never go over 50 pounds.
All right. You're unusual. What's the usually recommended rate of potassium in the fall? Your potassium chloride? 300? 200? 300? Okay, you have to remember potassium chloride is about 140% of the sodium chloride salt index. So if I'm putting out 200 pounds of potassium chloride, my potential salt effect is probably somewhere closer to 250 to 300 pounds of salt per acre. I thrive my biology. Salt is one of those really cool minerals that does this. It's great stuff. Okay? If you want an airport landing way in your field, put out a little extra salt. This will help get her there. Okay? And besides that, the salt will screw up every cell in your plant. So, the potassium chloride, I know it's a little bit cheaper than the potassium sulfate, but it's a tiny step forward in the checkbook, and it's a big step backward on your soil and your plant life. Okay?
Or what if they use potassium oxide? Potash.
Well, we need to look at the breakdown rate of it.
That's my question. If you put potash on, say, a week before you plant, is it going to be ready for uptake? And that fifth week?
Right here?
Yeah.
You can have some of your dries or your liquids. Your liquids will be available within, if we chelate them and we balance them, they'll be available in your plant in a week. Some of your dries, you're going to have 4 to 6 weeks head start on them.
It's too late.
It's too late. You're going to have to put it on pre-plant if you're going to use a dry. So you're going to maybe have to change the way you manage your fertilizer depending upon what equipment you've got. We sat down with some of the colony guys up in South Dakota, and the guy says, "Why can't I do this with dry? Why can't I keep using dry?" I says, "Because your dry fertilizers won't manage the peaks. You can't get it out and have it break down quick enough to manage this peak." And I said, the other thing is when you talk about a slow release fertilizer, what do you think it would cost to try to get all of your soil up high enough for 2 weeks, but you got to have it up there the whole year? My goodness, that's going to cost a ton of bucks. Maybe I'm better off to put in a little bit of liquid right back in here so that it's there in the root system, it's being held, the plant comes after it. I can manage a spike without overloading the whole system for all these weeks before and all these weeks after. But with dry, you're going to have to do that. It's going to be very tough to manage these spike weeks with dry. Go ahead.
You talk about using a liquid for a spike period like that, and I know some places that I would call for. Do you have any you recommend, like for potassium or phosphate?
Well, yeah. You know, you look at what your soil does and doesn't have. I mean, you can get the liquids. You can get potassium sulfate. You can get potassium thiosulfate. You can get 28%. You can get 32%. You can put out urea. I mean, there's a lot of different products. But the crucial thing is we try to manage the nutrients according to what the plant's after, not what's according to convenient for the co-op. That's where we're missing the boat here, guys. Oftentimes it's not that we didn't put out enough nitrogen. We didn't put it out at the right time. We put it out way too early, and we lost it. I mean, I am not a big advocate of putting out nitrogen 8 months before my plant wants it. Man, why? I mean, that's like opening the front door to your house and telling the guy that, you know, I got a lot of money in the safe. Yeah, I'll just be gone for a few months. You know, you going to come back and expect all your money to be there? I don't think so. The problem is soil chemistry plays a real crucial role in how you handle your minerals. I don't like my minerals on way ahead of time. What if I end up with 16 inches of rain? My goodness, you know, my goodness, you're going to lose a lot of your nutrients. And so nutrient timing plays a big role here. And there's a lot of products out there. I'm not saying this one's good or that one's bad. All I'm saying is we need to select products that are not as toxic, the ones that we can manage the best, because this plant is not going to change its diet to accommodate us. It is what it is, and if we're going to be on top of these yields and really get the potential there, we got to be on the spot ahead of time with the nutrients for it. That's the reason we put this together. Is we need some very specific targets of what we're going after. If we're going to change these yields, if we're going to get them past 200 and 250 and into the 300 range, we can't keep doing what we're doing. You know, the guys, again, I've talked to some of these guys that are putting 400 plus bushel of corn down, and they're feeding their plant over and over and over and over. One guy, 8 times a growing season. And what he's realized is my fertilizer has a functional life. And if I am going to get this yield, I've got to constantly keep something underneath that plant. And so I can't put something out one time and expect it to do the job for the next 5 months. It doesn't work. There's nothing out there that will do that. We don't want to go out there 8 different times, so we have the product that helps us neutralize our fertilizers, change those charges so they're not reactive and the plant has time to take them up when it comes for it. I would rather put out the nutrients 2 or 3 times than 8 times. I mean, once in a while it would be nice to go fishing in the summer. I can tell you a guy that's feeding his plant 8 times ain't getting the fishing time in. Richard.
Like when you said 8 times, is it for your feeding or side dressing?
You can't get enough in for your feeding. He's doing probably 2 side dresses. He's doing, you know, besides his pre-plant and his in-furrow, he's probably got as many on the ground as he does above the ground. But he's feeding it. I mean, they're feeding it right through tassel. Absolutely.
But the biggest to have a full-time guy on machine, whatever it is, put in the field on.
You know, the thing is, you can drive the yields, but there's a function of machinery and time. Okay? These plants will respond. They've got the genetic drive, and the system's intact. We just don't quite manage the fuel very well. So that's what we look at with these programs. Okay? You look at your nitrogen curve. You've got a big spike, and this is simply 150, 200, 250, 350, 400 bushel corn. You begin to see the nitrogen demand. You have a big pull here in vegetation, and you've got another little burst that comes back in the reproduction side. When you look at phosphate, you've got a different curve. This one is longer and later on in vegetation, and then it's earlier on in reproduction. Your potassium is completely different. Comes in hard here, week 6 and 7, comes down, I got a little spike here at tassel, come back up, reproduction. So when you look at them, you can see they're all flowing quite a little bit different. So we get a picture of this, we can manage it better. Your sulfur, again, this is coming in late. So we want to be able to deal with the sulfur. If I'm going to try to manage this with ammonium sulfate, I got to be on here 6 weeks ahead. If I'm going to broadcast ammonium sulfate out here, okay, I got to have at least 6 weeks before it's down into the soil where a plant can grab it. Okay? Feeding a corn plant, we've got fall and early spring. There's a lot we can do on these to build the base of our minerals in the soil. We've got manures, we've got soft rock phosphate, we've got potassium sulfate. These minerals can go out in the fall, they can go into the soil, and largely they'll bank and they'll be there by spring. You can broadcast, you can band it. If you band it, you can get by with less. You get that efficiency right in that zone. Some banding equipment, you can cut your fertilizer in just about half. Still produce the same yield. So the digester, this is taking the potassium and the calcium and the phosphate and the nitrogen that's in the plant residue, getting it processed by the microbes, getting it back into a plant available form as fast as we can. All right?
And it also avoids setting up an environment for pathogens.
Yep. It's a big player. These pathogens cost us a lot of money. And the fact that we've got them, it'll pay us to deal with them, Paul.
What's your game plan on managing this low residue program? We try to get that digester sprayed on immediately after that corn is harvested, as much sugar in that corn as possible, and get it incorporated in the soil.